Hey, Calc VC, good to see you again. Well, I'm not really seeing you, you're seeing me. So I just wanted to get us started with our review of AB material. As we talked about last week, BC really is just a little bit of an add-on to the AB curriculum. There's some few things along the way that we have to add in, but mostly just the stuff at the end. And so we will kind of go through the review somewhat quickly, but since it is all part of the test, I do want to make sure that we understand all of the stuff that comes in the AB section. So I've got my fancy little virtual whiteboard here, and we're going to jump right in here. And the first thing I want to do is sort of remind you all how the College Board asks us to think about everything, and that there are certain tasks or ways that they like us to be able to explain our thinking. Specifically, I'm talking about GANA. So the first thing we're going to do here to start off with is we're going to review the GANA acronym. So it's G, which you may remember stands for graphically. The N stands for numerically. The A, I guess you could say analytically. Sometimes I think of that as algebraically, but it's not always just algebra. So maybe analytically is a better way to put it. And then the W, as you know, vertically. All right, so I know that's not really a word, but you know, it makes it flow. All right, fine. We want to be able to explain our thinking and reasoning in words. And so those four different modalities that we're working in calculus really are important in Calc BC. So when you're doing your justifications, you know, if we're doing something graphically or numerically or analytically or in words, we want to be really, really careful with our language. Last year, you know, the calculus exam was a little bit different with the online stuff, and I got to see my students work for the first time on an AP prompt, and it was eye-opening in some ways to see how some of the different modalities really challenge some people to be able to put down proper justification. And when we get to those points, I'll kind of highlight them along the way as we work through this. So the justification step is going to be pretty important, and it'll be something that you're assessed on frequently here with Calc BC. So without further ado then, as all good calculus classes do, we're going to start with everybody's favorite, that first idea that Newton had to come up with because the mathematics of his day just didn't work for physics. So the idea was limits. All of calculus, as you know, can get reduced down in some way, shape, or form to a limit. The idea that we could have motion at a single point in time, that you could have area below a single point on a curve. All those ideas stem from limits. And so, so we are going to start off with this idea of limits. And as you know, everything in calculus is sort of the underpinnings of all of that stuff is limits. When Newton was worrying about calculus or developing calculus, he was really frustrated because the mathematics of the time did not really allow for him to solve the physics problems he was working on. So he had to invent limits. So we're going to review kind of what do we mean by limits. So, you know, what do we mean? And then how do we find them? Oops, find them. And finally, when do limits not exist? Oops. So those are kind of our three main topics for today. And then we'll get a little bit more on limits in our next video before we jump over to talking about continuity and how limits will impact that. So let's start off with what do we mean by a limit? As you probably really remember from last year, whether you had myself or you had Mrs. Stuckey, what we mean by a limit is that as x approaches a value on the x-axis, what is happening to the corresponding y value for our function. So I'm going to draw this function, and you're probably going to get real tired of me drawing this function. And for those of you who had me last year, you know that's my favorite shape of function to draw. And so I'm just gonna pick any old point. I'm gonna just call the point C right here. So that's a point on the x-axis. And so it has a corresponding y-coordinate up here, which we're gonna call f of c. And remember that as when we write the mathematical symbol out, when we write limit as x approaches c of f of x, okay, we're not so much worried about what happens at c, right? It's not about that. It's not about f of c. It's not, f of c doesn't even have to be defined, okay? We just want to know what is the value or what does the tendency of that function doing as it gets, as the x coordinate gets closer and closer to c, when the domain value gets closer and closer to the coordinate c. And so what happens? To the y value, oops, as x approaches c. That's what we mean when we're talking about a limit. So f of c can be undefined, f of c can be defined, it doesn't matter. We are just interested in what's happening to the values on the y-axis as x gets really close to c. And that was the definition we kind of worked with most of the year. There was a particular mathematician, his name was Cauchy. He didn't really like that definition. He felt it was a little too wishy-washy. Like what's happening to y? Like what value is y approaching as x is approaching c? What do you mean by that? And we're going to actually have to dig into Cauchy's definition and proof of a limit a little bit later, because that, unfortunately for you guys, actually shows up as a BC topic. So, hey, good news. We're going to get to learn how to do that proof. So, but that's a video for Wednesday, not for today. So, so just a reminder that that's the general idea of what we're talking about as a limit. And then we're going to look at how do we find them. So how do we find them? Okay. Now, if we were in class and we were live, of course, I'd say, hey, who remembers how to find limit? Give me one of the techniques that you know how to find limit. And we can't do that right now. So I know one. It's called direct substitution. And that is my favorite way to find a limit. Of course it is, right? Because in direct substitution, all you do is you directly substitute the c value in for x in the function, and you can just compute it. So for example, I won't waste too much time with this, but I do need to do one example of each of these just to make myself feel better. X approaches 2, okay? And so I'm going to write the function here instead of f of x, and it's x squared plus 1. And you can see, because there's no discontinuities or anything, that I am clear to just go ahead and enter 2 directly into the function, x squared plus 1. And so you would get 2 squared plus 1, or you would get 5. So that's direct substitution. That is probably my favorite method for finding limit because it is the simplest. And I'm all about things being simple. However, sometimes we can't just direct substitute. And you know that there are some other techniques for that. Cancellation was a real popular one. When we first started out, we said, okay, so maybe your function actually has a discontinuity in it. Okay, so I'm talking about like the limit as x approaches 1 x squared minus 1 over x minus 1. Because at that point you go, oh shoot, I can't direct substitute because I would be dividing by 0. Hey, I took some algebra classes back in the day and I remember something about that numerator. It's factorable, like so. And sure enough, you cancel the discontinuity out of there, and now you just direct substitute, and you get limit as x approaches 1, x plus 1 is 1 plus 1 equals 2. So that is an example of an algebraic technique. And there we go. These are, if you remember from the GANA acronym, the analytical way to solve things. These are a couple of examples of analytical ways of finding a limit or explaining a limit. This third way is also analytical. Rationalization. I'm running out of room here, so I'm going to write this one below it. In the rationalization technique, remember that we had some sort of probably a square root or something that was going to cause a problem. So if I go down here and I say, hey, I'm going to do the limit as x approaches 0, and I've got x over the square root of x plus 1 minus 1, and I realize, oh shoot, yeah, I can't just put in 0 into this because then I would also be dividing by 0 again. Well, the rationalization technique says, don't worry. You can multiply by a conjugate over itself, because really that's just multiplying by 1, right? And notice what happens when you do this multiplication. Okay, the numerator, I'm going to just leave it x times the quantity square root of x plus 1 plus 1. And when you multiply these together, because they're conjugate pairs, you get x plus 1 minus 1, right? A squared minus b squared. Well, hey, check it out. That's x times the square root of x plus 1 over x. Your x's will cancel. And now square root of x plus 1 or 2. If x is 0, you can direct substitute now and get 2. And so those were kind of the three main ways we learned. First, to verify or to prove a limit or to explain a limit analytically. Okay. Then remember there was that weird one, the squeeze theorem. Okay, yeah, we have to review that guy. He is going to show up again. And squeeze theorem, number 4, so in the squeeze theorem, right, we were trying to evaluate a limit, but the limit was tricky because we couldn't evaluate it directly, okay, for some reason, right? So what the squeeze theorem said, hey, look, it says if you can tell me a function that's always less than or equal to your function, and you can tell me another function that's always greater than or equal to your function, okay, and if those two limits are the same, if the limit as x approaches c for h of x is equal to the limit as x approaches c for g of x, they're both the same number. Let's call it L. Okay. So look, F is squeezed in between those two. I like to draw this one sometimes to show like I might have my function. Oh gosh, let's pick a green color for h of x here. So h of x might be doing something like this. Okay, that's h of x. I'll write that on there actually, h of x, because it's lower. And then g of x is greater, so it's coming in like this. There's g of x. Well, now think about it. Is there any way I can draw f of x so that it's greater than both those? You know, it doesn't matter what it's doing. Maybe it's wobbling around, right? But it's got to go through that point where all three of them meet, right? They all have to have the same limit L right there. So, oh, I didn't change the colors, but you get the idea. That was the squeeze theorem. Now, when we did that section, well, okay, so if you were in my classroom, when we did that section, I said, look, there's really two main things you need to remember from the squeeze theorem, okay? One, or A, is that the limit as x approaches 0, sine of x over x. You guys remember? Sine of x over x? Come on, guys, you remember. It was 1, okay? The other one was the limit as x approaches 0 of 1 minus cosine x over x. Remember that one? Yeah? It was 0. Okay. I didn't necessarily want you just to memorize those two, but I know that's what a lot of people do. It's totally fine. Those are the outcomes that we were like, oh yeah, that's all we need to know with squeeze theorem. Well, that works for AB. But for BC, you probably want to remember all of this junk as well up here, because you're going to need it. Later on, we're going to be doing some work, and the squeeze theorem is going to come back. And we're going to see how the squeeze theorem can help us with some other work that we're doing much later on in chapter 8 when we get to that. All right. Some of you are probably going, well, wait a minute. I seem to remember something about indeterminate forms. And you are right. There was another method. We didn't learn it right then, right? We couldn't learn it right then because Hopitals Rule, oh yeah. Hopitals Rule requires that you know how to take a derivative. And since we didn't know how to take a derivative at that point in the year, we couldn't really talk to you about Hopitals Rule. Now, you all remember how to take a derivative, I'm sure. If not, don't worry, we're going to review it later. But Hopitals Rule said this, said, hey, look, if the limit as x approaches c of f of x over g of x is indeterminate, okay, remember that? 0 over 0 or infinity over infinity. Then the limit as x approaches c of f of x over, oops, forgot the c, over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. And that was L'Hopital's rule. And that turned out to be really helpful, right? Because it suddenly made some of those other techniques, cancellation, rationalization, even squeeze theorems, sort of irrelevant. Because notice in my examples, hey, look, x squared minus 1 over x minus 1, as x approaches 1, right? That's 0 divided by 0. So this would have been a L'Hopital's case. Okay? X over the square root of x plus 1 minus 1. As x approaches 0, that's 0 over 0. This would have been a L'Hopital's case. Okay? Even the squeeze theorem result. Sine of x over x as x approaches 0, that's 0 over 0. So L'Hopital's rule actually rendered a lot of those previous analytic techniques sort of not worthless. I don't want to say worthless because they're important, but maybe not as easy. And so I really like L'Hopital's rule. What I want to caution you about is that when you're employing L'Hopital's rule, your notation, okay, is important. Because this equals sign, this is not strictly speaking the same function on both sides, so you have to be careful. You always want to write by L'Hopital's rule in there, okay? It's fine to abbreviate it LH. The College Board readers, they understand what LH means. So if I was actually doing a problem, let's just say that squeeze theorem result, that first one, if I was doing the limit as x approaches 0 of sine of x over x, I recognize that that's 0 over 0. I would just write equals, and I'd write by LH limit as x approaches 0. Now, how's your calculus brain doing? Is it warmed up yet? What's the derivative of sine? And so, and of course, cosine of 0 is 1. So this is 1 divided by 1. So that is L'Hopital's rule, and that's the application that we were, or the how we used that back then. So that's it for today. So I just wanted to review really quickly with you that bit about GANA, and then about our rules and our techniques for finding limits analytically. So we talked a little bit about graphically. We talked a little bit analytically. Numerically, I'm not going to make you sit through me doing a bunch of punching in numbers into a T-chart and seeing what it gets to, because you all can do that on your own. All right. So that's it for today's video. The homework and the lesson that we're going to work together on Monday is all about using these techniques to evaluate limits. You are, of course, welcome to use L'Hopital's rule, but I want to caution you that you should probably try a few of these without L'Hopital's rule, just because they do come up in Calc PC as a technique you need to show. All right, with that, I will say goodbye. These videos are only supposed to be 15 minutes. I know this one's a little longer, so I apologize for that. I will try to do better as we get going along this year. All right, thanks, guys. I'll see you in class on Monday.